So, as we know, the cosmology is now in a crisis in the sense that some of the observations don't fit each other. So, for instance, the expansion rate of the universe when observing with galaxies and the redshift of galaxies doesn't fit the expansion rate when using the cosmic microwave background radiation. Also, we can see with the James Webb Space Telescope, we can see mature galaxies and mature objects such as black hole in the deep universe, and there's no explanation why these objects even exist. But one single explanation to all of these tensions is that the distance measurements are biased. That means that when we observe the expansion rate of the universe with galaxies and the redshift, if there's a bias, maybe that expansion rate is not exactly accurate because of that distance bias. And that can also explain why we see mature objects in the deep universe, because maybe their age relative to the Big Bang is not exactly what we think it is. So that is one explanation that can explain all of it. There's no really theoretical explanation to that, but what I'm doing here, I'm trying to see if there's an empirical evidence to that. And one of the problem is that if such distance measurement bias exists, it means that it means that it exists in all of them. All of them are biased, and that makes it difficult to identify such bias. For instance, if the redshift is biased, and the redshift of all galaxies are biased, and it's difficult to compare. So what we have, we still have one way that I can think of that we can do analyze such bias, and that's what I'm going to show here. And I'm going to show it also with explanation of how to reproduce those data, how to, I'm going to show the links to the data. We can use the data, access it, reproduce all the results, and see that the distance measurements that we use are indeed biased. And the bias becomes more substantial when we go deeper into in the universe. So it's not substantial for the local neighborhood, but it becomes more substantial when we go deeper. So what we can do is use the rotational velocity of the Milky Way. So the advantage of using the rotational velocity of the Milky Way is that that is a verified velocity of about 220 kilometers per second. So we know that it exists. It's not based on assumptions. We know it's verified velocity. And we know that redshift corresponds to that velocity, so we can use that to test, for instance, the consistency of the redshift and the consistency of other measurements, such as the brightness. Now, we cannot do that with a single galaxy because we don't have the baseline for a single galaxy. But what we need to do is do it statistically on a collection of galaxies, population of galaxies, and then we can see if the differences between the redshift of galaxies that rotate in one way relative to the Milky Way compared to the other way, if that rotational velocity of the Milky Way, how does that affect the redshift that we measure? So what we have is a population of galaxies, and we measure galaxies that rotate in the same direction relative to the Milky Way are supposed to be dimmer, and a little bit of higher redshift compared to galaxies that rotate in the opposite direction relative to the Milky Way. When you have a population of galaxies, we can also compare those differences and do it in different redshift ranges to see how it changes with the redshift or with the distance. So here's a first experiment or sets of experiments. What we have here, the different telescopes and different analysis methods. They all explain in the paper specified below. And all of them show that the redshift of galaxies that rotate in the opposite direction relative to the Milky Way is a little bit lower compared to redshift of galaxies that rotate in the same direction relative to the Milky Way. But what's interesting is that the difference is higher than the difference we expect to see. So that is already an indication that something is happening with the redshift that maybe it's not exactly completely taken into consideration in the current redshift measurements that we do. But let's look deeper into it. Before we do that, that's some data from third-party data sets. And these are data sets that have nothing to do with me. I didn't prepare them, but if you analyze them, you see exactly the same results. You can access them. They're public, been around for over a decade. Just the people who created them just never thought of testing that. All of them are publicly available. So the data set that I showed in the previous slide, all of them are publicly available in the paper specified. There are URLs. You can get all those data sets and reproduce all of those results. Just make sure that the data sets are also clean and that the results are exactly the results that I show here. So it takes minutes to do those experiments. It's really easy. Here it becomes a little bit more interesting, maybe, that we use here now the data from HSC. Now, HSC has a smaller footprint, but it's a bigger telescope, so it goes deeper. And what we see here, we can separate it to different redshift ranges, and we see both in the South Pole and the North Galactic Pole, the red line and the pink line, both of them show that the difference in the redshift increases when the galaxies are more distant. And it's consistent. We have three different redshift ranges here. We see it very consistent in both the South Galactic Pole, North Galactic Pole. And that is unexpected because the rotational velocity of the Milky Way does not change, is constant regardless of the object that we observe, regardless of the distance of the object that we observe from Earth. So that is not expected, but what we see is that the difference in redshift increases as the objects are more distant from Earth, and that shows that there is a bias, and the bias increases. Not just there's a bias, the bias increases as the objects are farther from Earth. So if that trend continues, it's only until redshift of zero point 0.3. So it's not that deep into the universe. But if that trend continues, that can explain the HO tension and those mature galaxies and the other anomalies that we see. And we can do the same thing also with the photometry of the brightness of the galaxies. Galaxies that rotate in the opposite direction relative to the Milky Way are supposed to be a little bit brighter than galaxies that rotate in the same direction relative to the Milky Way. The difference is not substantial, it's not huge, but it's not zero. So we can still use it to do the analysis. Here are some examples from Sloan and Hubble Space Telescope, two different analyses. All show differences in the brightness. Galaxies that rotate in the opposite direction relative to the Milky Way are indeed brighter. It's interesting that with Hubble Space Telescope, the differences are larger than with Sloan Digital Sky Survey, and Hubble Space Telescope is obviously goes deeper in space. So we do see the same trend that we saw before, with when we look deeper into the universe, the differences are getting bigger, although the rotational velocity of the Milky Way obviously stay the same. And that's analysis with the Legacy survey, a very large number of galaxies, and you can see the same observation, the same difference in the magnitude in the different bands. And that's with third-party data from Galaxy Zoo in this case. Maybe not the best data ever, but it's very easy to do that experiment, cast jobs. You can do in 5 minutes, you can run a query and see these results as well. And that is analysis with HSC. Again, can go deeper in space. So where we can separate it into different redshift ranges, galaxies that are below a redshift of 0.1 and galaxies that are at higher redshift than 0.1. That data, unlike the other data set that I showed, that data has not been published yet, but you can access it in the URL here below in the slide. So there's no paper yet for that, but you can access the data, you can reproduce it very easily. And what it shows here, just as before, that when looking at closer galaxies, we don't see that much of a difference. The difference is not so substantial, so significant. But when we go farther, when we go to redshift larger than 0.1, then it becomes statistically significant, and we can start see that. And here's analysis of the flux. That's also interesting. So we see that we can compare the flux, the flux difference. That's the difference of the flux between galaxies that rotate in the same direction relative to the Milky Way in the opposite direction. And we can see that the difference in the flux that it stays pretty much the same when comparing galaxies that are closer to Earth and galaxies that are farther to Earth. That's something to look into. It could also be a coincidence. It could also be a coincidence, but that's definitely something to look into. It means that the effect is stronger on galaxies that are in the distant universe. That can explain why galaxies in the distant universe that rotate in the opposite direction relative to the Milky Way are indeed brighter than galaxies that rotate in the same direction relative to the Milky Way. And if that is the case, maybe it can solve the Hubble tension. And let's see, here's a small attempt to do that with a small number of galaxies from the SHOES catalog. So what you see here, when just using galaxies that rotate in the same direction relative to the Milky Way, the HO tension is decreased substantially. So it gets to 69, very clearly within statistical noise difference from the expansion rate measure with the cosmic microwave background. When using just galaxies that rotate in the opposite direction relative to the Milky Way, the Hubble tension becomes stronger. So again, this is done with a very small number of galaxies. You can see with 22 galaxies and 36 galaxies and one a supernova. So these results need to be further we need further work to see if that's consistent, but it's an indication. It's some indication that if we indeed use just galaxies that rotate in the same direction relative to the Milky Way, the Hubble tension is solved, which means that that is a candidate for an explanation for why we see this puzzling tension. So what other explanation we have here? So the distance measuring bias, that's the leading explanation, at least in my opinion. That's what I think, what explains it. We can also look at those observations as indication for anomalies in the large scale structure. For instance, indication for rotating universe. That's an old theory that is getting a little bit of momentum recently. It can also be an indication of black hole cosmology. And black hole cosmology, we can see it as a superset of a rotating universe because black hole cosmology also assumes a rotating universe. So these can also be options, although I tend to believe that a distance measurement bias is the likely candidate for an explanation here. And it explains also, it fits very well with the other tensions that we see. These are the references. Thank you very much for listening.